Okay, so like I said before, how it started. So one of my here with this project, and he told me like, this is some cool stuff going on. Did you saw this project or not? So he
O with the IIO subsystem of the Linux Foundation, but by the time there's other, so I am in this project, and they have a ton of contribution to the kernel, and then the Cypher project comparing to me having nothing. So, anyways, because the Linux kernel mainly is
I know he's glad to solve schedule time, schedule time. Uh,
You need to keep you need to click selection. Oh, yeah. Hello, test. 1, 2, 3. Test. 1, 2, 3.
One, two, three, one, two, three. Okay. Excuse me. Can you change?
One, two, three. 1, 2, 3. Test. 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 1, 2, 3.
Yeah, it's work also.
No, 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 no.
No, this is
Is it Chris? You want me to check?
It's not how it's frozen.
Okay, you want to present from this one? Right,
So the laptop was
you
not
connect to the so did you connect to the screen yet?
I guess
Sorry.
Right.
It's only training to right.
Yeah. Yes, yeah.
No, not that one. This one. No, I was just click the signal, but it doesn't work. This is it's going. Sorry.
Right click.
Good. Uh, this one. Yeah, can you click on stop? Oh, thank you. Right. So you need to get to your.
Wait one second.
So, what is the difference between the open source and the proprietary firmware? So we can customize the boot screen to have the component logo, whatever you want, and I've added the always on Bluetooth low energy, so you can do the streaming and a lot of things like config and control, remote control, and so more feature uh, have added into this firmware. So it's open source, so everyone can come and learn, use, and add more feature into it. So usually, uh, I think the firmware should be kept simple because it have limited resource. We can add, we cannot add complicated stuff, but because it's open source, people came and add some more feature, making it over engineered. It's over engineered, but somehow it's a good thing anyway. So here is the open source hardware. We compared to the proprietary hardware without the battery connected uh, to any to make the firmware upgrading easier, and people came and request to add the two button and external storage to store the game and playing game easier. And we also had a microphone and one and this version this came from FrostCon 2024 and it's asked for a misfit switch for privacy. Yeah, and this is the feature that added more compared to the proprietary hardware.
Yeah, so we have a particular Flickr application for the badge magic. So I'll be probably giving a very high-level overview what this application does and how it transfers all those data to the badge. So this application contains basically two sections. One where we connect to the badge and transfer the data to the badge, and other where we formulate this data. So connecting to the data badge is because it's a Bluetooth low energy device, it's very easy. We just need to search for the badges with a particular service UID, and then we search for a particular characteristic UID to send those data to the badge. And comes to the other part where we formulate this whole data. We have these two sections in it. One where we handle only text, and other where we handle the images also. So how we are currently handling the text is we have a hash map for the text, then we map each character with their hex values. And then when user types some text, we take those hex values, we add them together to form a string, and then we convert the string to a byte string or byte array. And then we send this byte array with a particular image to the batch. So this is something which we will be changing very soon, and we would like anyone to contribute to it, because right now we are constrained to certain sections of certain types of characters. Only the characters that are in the map. We could probably figure out something by which we can support any character to it. There could be hundreds of ways to do this. So, and the next section is where we handle the images. And so, handling images is particularly straightforward. What we do, we took the images, we scale it to the size of the batch. So, whatever the image size does not matter, we scale it to the batch size, and then we bring those images to get only the pixels that are required for that image. So, suppose there is a white background and the image is somewhere in the top left. So, we would probably need only the top left section or only the image section over there. So what we do, start to loop over the whole image, and we try to find out where the image starts from each side, top, left, right, bottom. And then we trim out that image. So image is scaled to the back size, and then we have the trim image. Then we convert this trim image to a byte array and send it to the batch. So that's the whole working of how this Flutter side of Batch Magic works.
So have to
So we would request most of you to just try to contribute. We are so much open issues over there. We need someone who can actually add some more animations to it, because we have 6 or 7 animations right now, but there could be probably more. You can come up with some new ideas, some new animations also. And then there are these cool new features that are coming up, like we are going to add this audio visualizer to it. So you're wearing a badge, you're listening to some music with the sound. The badge will show these lines according to the sound that is going around you. So these are 10 of new features coming very soon. And I'll probably be having a session on how to handle the images, particularly further, tomorrow, just before lunch. So I will probably ask you all to come up, because it's going to be an interesting session. I'll be diving deep into specific Flutter things about this application and how we can handle these images and how we can use this particular image handling in Flutter to different sections or different parts of the application also. So yeah, that's it.
Yeah. So there's a mic on. There's a microphone on the hardware, so you can make that audio visualization, and if you add a accelerator sensor into this, you can make a fluid simulator, or you can both zoom, or you can play basketball on it. So if you own one of these bags, you can join me the workshop on 15th at 11:30 to burn the open source firmware into the bag. We'll be showing how to upgrade the open source firmware to the bag and how to hack this bag. So hopefully we can make some bag actually burn tomorrow.
So we will be having this session tomorrow at 11:30. It's going to be very interesting hands-on session where we'll open up this batch and try to flash the new firmware to the batch. So I request you all to come to tomorrow's event also. Yeah, thank you.
Thanks a lot. Any questions? The other people for the next. Did you have okay.
Testing.
Right, well, I need to.
Yeah.
I want to yes.
Yes. Okay. And then if I just screen. Okay.
Hi everyone, sorry for the technical difficulties. We're moving on to our next talk. Challenges of unit testing hardware drivers is by Alexander Smith. Without further ado, I'll time credit.
Right. Thank you. Can everyone hear me? Hear me well? All right. Great. Okay. So I'm Alexander Bestman. I have been the maintainer of the Pocket Science Lab Python library, among other things, for the past 5 or so years. And during that time, I have learn some things about testing hardware adjacent software that I would like to share with you today. So I'm going to go over these points. Why is it difficult? How can it be done using PSA Python as an example? Spoilers alert for that is that the way that we used to do it in PSA Python is no longer how we do it today, and I will explain why. I'm going to go on a bit of a detour, explaining or investigating, discussing why should we even unit test hardware drivers in the first place? What is the benefit? After trying to answer that question, I'll get back to the how, and finally some key lessons. So first of all, why is it hard to unit test hardware drivers? And just note on terminology. When I say testing throughout this talk, I mean unit testing unless I specify otherwise. The reason it's hard to test hardware drivers is state. Hardware is stateful, and state is difficult to model. Like ideally, when you are writing software tests, you want this situation. You want to have like a function or a class or something like that that takes some input, does something with it, and spits it back out in a neat deterministic way. So you can just check in your test: is the output what I expected? If it is, good, the test passed. If it isn't, bad, the test failed. But in reality, when we're dealing with stateful systems like hardware, we have this situation. You put something into the function talks to the hardware has state, sends something back, which we don't know because it's difficult to model state. It's technically deterministic, unless it's like some kind of quantum random generator, but it's very difficult. In practice, you can't know what state the hardware is in. That means we don't know what our expected output is from this function. So we can't test it in this manner. How can we deal with that? Well, the most obvious way is to just keep the hardware in the loop. But if we do that, the tests become sensitive to the order in which you run them, because the tests themselves, when you run them, affect the state of the hardware. The tests become sensitive to hardware fault. If something breaks, your tests will fail, and it's not going to be immediately obvious why they're failing. And a significant problem for open source projects specifically, like the Pocket Science Lab, is if your tests depend on having access to the hardware, you are basically eliminating the possibility for new contributors to contribute to your software because they don't have the hardware. And this type of testing, where the hardware is present in the testing loop, is not unit testing. It's integration testing, which is also good. That's something you need to have. But you ideally also want unit tests. Perhaps I should mention that what unit test is, if someone is not familiar with that. The idea with unit testing is that you subdivide your software into small, individually testable units. Yeah, and I'll get back to how you do that in a bit. So as an example, this is the current sort of software stack or architecture of the Pocket Science Lab. Over here is the user. The user interfaces with the, in this case, PSA Python via one of these instrument drivers, which in turn talks to the UART driver, which talks to the hardware. So when the user puts something into, let's say, the oscilloscope, okay, I want to get some samples from the oscilloscope. This module calls the UART driver, which sends some bytes over to the hardware, which does something, sends some bytes back, which are handled by the UART driver, which then return those to the oscilloscope module, which does some post-processing and hands the output back to the user. This is the case for every instrument. And that means that each of these modules is stateful because each of them calls the hardware, albeit indirectly. And that makes all of these very difficult to test. Because each of them is stateful. So one of the first things I did when I started contributing to PESA Python about 5 years ago was I added a test suite, like a way to eliminate the hardware from this test loop by recording the bytes sent by the UART driver to the hardware while we were running integration tests. And then when we wanted to do unit tests, that is without the hardware present, we just replayed the exact same bytes that we got during integration tests. So this eliminates, theoretically, the need to have the hardware present to run the tests. This worked well for some situations. Like one thing that it is extremely reliable. So if these tests pass based on the recorded traffic, you can be very, very certain that nothing has broken. Like if you send the same bytes to the hardware will respond in the same way. So this is, in that sense, it's actually a very good test, because you know that if the test passes, you can be certain that your driver is still functioning as intentional. It's also low complexity. Like mocking interfaces is a notoriously difficult problem. But just recording and replaying traffic is really very simple. Yeah, there's no real need to like model internal hardware states. You just record and replay. So in that sense, it's both reliable and simple. But it has some drawbacks, some quite significant ones, it turns out. This added very significant maintenance overhead, this approach. Basically, the tests became too specific. Very, very minor changes in the code resulted in a need to re-record not just like one test, but in many cases, lots of tests. Because something like if you change something in the UART driver, every single test just started failing. And yeah, then that's something that a maintainer, meaning me, had to go in and even re-record, re-upload the recorded test data for basically every little change. So that was pretty annoying. And in practice, it turns out it didn't really eliminate the requirement to have access to the hardware, because again, if every change breaks the tests, then you can't actually make use of the tests again unless you have the hardware. As a case in point, this is a pull request against PESA Python. It's super simple. This pull request fixes a problem. It's not really a problem at all. This already worked fine in Python, but basically there was a difference between the Python and the Java implementation of the triangular waveform function, because Java and Python handles the modulus operation differently. The details aren't important. The point is that this is a super small, trivial change. And it resulted in this really long, well, it's not really long, but it's like kind of significant discussion on like back and forth. This isn't working. Why isn't it working? The tests aren't passing. Okay, and yeah, basically lots and lots of maintenance overhead for like trivial changes. So we ended up abandoning this approach. We no longer use this recording, replaying-based unit testing. We still use the integration tests, but not the unit tests. It worked well, but added too much maintenance burdens. So at this point, we're going to take a step back and ask ourselves, what is even the point? Why do we want to test the hardware driver? Like, what is our goal? What is our end goal with that? So is it this? Is it that? I mean, honestly, I'm going to be honest with you. This is definitely something that I want. It looks nice. It looks really nice on the GitHub page, but it's not a really good reason to test. Like that shouldn't be the core reason. Company policy says so. I mean, if you work for a company, your boss tells you got to have unit tests. You're gonna write unit tests. But why does the company policy say so, though? Do we test software to make sure it works? Is that why? Yes, yes, in the sense that, you know, the chicken crossed the road to get to the other side. Yeah, okay, we test software to make sure it works, but like that's not like a good answer to the question. It's true, but it's not a good answer to the question. It doesn't really explain anything. So, attempting to answer the question, every software exists on a scale of like severity of you know, worst case scenario. If the software stops working, if the software breaks, what is the worst thing that can happen? On one end of the scale, like the user is like kind of annoyed, right? The software isn't really doing anything very critical, but it broke and the user is annoyed. Okay, on the other end of the scale, the user dies. Uh-oh. Depending on where your software is on this scale, the answer to the question why test software will be very different. On this end of the scale, the point of testing, I would say, is that it saves you as a developer time. Like you can sort of stop thinking about whether every little change breaks your software, and that relieves you. It lessens your cognitive overhead unless you focus on writing better software. Whereas on the other end of the scale, the point of testing is to not kill the user, right? This means that if you're on this end of the scale, you have to accept that testing, like you must test, even if testing turns out to be very difficult, even if testing adds very significant overhead to your maintenance burden, you still have to test. But most software, at least, let's say, open source software, the kind of thing that we're dealing with here, probably leans towards like this end of the scale. And that means that you actually have the luxury of deciding sometimes maybe it's not worth testing every single thing. And this is true for all software on both ends of the scale. Testing your software encourages developers, that means you, to write testable software. And this is extremely important. This, I will argue, is the single most important property of software testing. Making you, the developer, think about your interfaces. Is the software I'm writing testable or not? That, unfortunately, or maybe it's fortunate, I don't know, is very difficult to like quantize. You know, test coverage is easy to quantize, and anything that is easily quantizable falls into Goddard's law, which is when a measure becomes a target, it ceases to be a good measure. So again, that 100% coverage is like, it looks very nice, but it's not a good target for, like, it doesn't actually tell you much, if anything, about whether your tests are good. So this is kind of okay, tongue in cheek here, but when you're first starting out as a software developer, you don't have a whole bunch of tests. You're just writing software because it's fun and it kind of works. And if the build passes, you're like, good, I'm happy. And then as you grow as a developer, you add, you know, your GitHub page starts looking like this. You add tests and linters and all manner of things, and eventually you sort of tip over and realize, maybe I don't need all of this. I'm not saying that you necessarily go back to this, but like there is a cost. There is a cost to doing all of this, and if it's not paying, if that cost isn't paying you back in terms of like writing better software, you should stop doing it. Anyway, getting back to the how of how to test hardware drivers, or really any stateful software. The problem with the PSI Python architecture is that the entire thing is stateful. And the way to fix it, so this is something that is like a work in progress. We're not quite here yet, but the way to fix it is to move the statefulness closer to the hardware. You can't really remove the statefulness entirely because it is a hardware driver. It has to keep track of what the hardware is doing. Somewhere in the driver, there's going to be some kind of model of the hardware, and that is stateful. But you can refactor a lot of it to not have state, to be stateless, deterministic. Like instead of the user calling the oscilloscope, that propagating all the way down to the hardware and all the way back up, you can use a dispatch model with the loose coupling, which uses like individual functions like this to pre-process the user input, turn that into something that you can send to the hardware via the UART driver. And once the hardware responds, you don't propagate that back up to the same function. Instead, you call like something else. And in this case, all of these just have a very simple input-output deterministic stateless, easily testable. But what about this part? We still have states. How do we test this? Now I'm going to say something potentially controversial. Maybe don't. Like I said, when we're writing software that is not safety critical, that is not going to kill the user, we have the luxury of actually thinking about, does a test help us, the developer, write better software? Like we could test this. It's perfectly possible to like mock this. You could use either the record replay that we used previously or some other form of mocking. But mocking is inherently complex. It adds a lot of complexity. It adds maintenance burden on you, the developer, that could be better spent elsewhere. And that is a difficult balance to find. But one of my sort of key lessons in this is that sometimes it's okay to not test hard to test parts of your code, because you can spend that effort elsewhere and make the software better. If you do that, though, you have to make sure to keep this part small and simple. Like the implementation can be simple even if it's difficult to test, simply because it has state, like I said. But if the implementation is simple, then it still doesn't add that much cognitive load on you, the maintainer, to think about, okay, when a change is made to this part of the code where you don't have a test, the code is simple enough that you can still just reason about it in your head without too much of a cognitive overhead, and still be like confident that the change doesn't break everything. So key takeaways, lessons learned from this. How do we test hardware drivers or any stateful software? There's no shortcut to this. You do it by writing testable software. Like if you're inheriting a legacy code base which doesn't have tests, and you're thinking to yourself, okay, I want to add tests to this. Don't. Maybe add some tests, but don't like go all out. Don't try to test something which is not neatly subdividable into units. You cannot unit test software which doesn't divide into units. You just can't do it. What you should do is, maybe write a few. They're not really unit tests at that point, but more like integration tests to make sure that you don't break anything too badly into something that is unit testable. That is how you test hardware drivers. And the reason why you want to do that is because you want to write testable software, because testable software is maintainable software. The single most important property of tests, in my opinion, is not to show you in like automated testing, okay, something broke. That's important. It is important for tests to do that. You're making a change or you're reviewing a pull request or something. The tests tell you, okay, did this break something or not? That's super important, but this is more important. This is the most important property of testing. They make you think about your architecture. Is it testable? That's why you should have tests. Okay, final points. Stateful software is hard to test. Testable software is maintainable software. Tacked on tests, which is sort of what we did in PSLab Python. They may be worse than none at all because they make you, it slows down development. If you have to stop and fix all of your tests for every little change, those tests aren't worth it and you should not do them. Tests should decrease maintenance load. Otherwise, don't bother. The exception to this is if you're on the very, very right end of the scale that we saw earlier, right? If your software can kill someone, the maintenance load doesn't really matter. You gotta test anyway. But usually that's not the case. And 100% test coverage is often not worth it. And in fact, I would almost consider it code smell. It's not really code smell, but you get the point. I'm very, very skeptical these days of software which claims to have 100% test coverage. That's probably something fishy going on, in my opinion. All right, so that's what I had. If you're interested in the PSLab, they're available for sale from the front desk. I think they're 1,500 baht. If you want to play around with them yourself. Tomorrow, we also have a series of workshops on the PSLab if you want to test them out, get some hands-on experience with them. Yeah, so I think we have time for some questions if you have any.
Anyone has any questions? We'll pass you the mic. Okay.
No.
So
Yes.
So like, is it also like some like, do we also have tests for the firmware? Like, or is it possible that we also move some power tests to the firmware so that it can dynamically respond if something on the layer has been?
That's a really great question. So currently in the PSLab, we don't have tests for the firmware. The reason for that is that the firmware doesn't build for any target except the actual microcontroller. So we can't like build it with GCC at the moment. So the only way we could test the firmware is using like a simulator, and that first of all is not a unit test; it's some kind of integration test. And the simulator is like proprietary, so no, it's not worth it. But we should. Like one thing that I would like to do with the firmware is to make it so that, yeah, it's more modular, so that you can compile individual modules using GCC and then test those modules. That is something that could be done, and that's something that we should work towards. Yeah. Okay.
I didn't see this.
Thank you very much.
Yes.
Right. Okay, it's all right. All good? Okay.
Yeah, in case your people come in.
Yes. Yeah, okay, that's great. Yeah, no problem.
It's not testable with the same.
what I've got to show in order of size and move backwards so that most of it is functional rather than depending on. This is more difficult in the hardware because you have like two, you have both the interface from the serial and you also have interfaces towards the actual like ADCs and things like that. Sorry. What we should do is we should try to do it faster.
Oh, what? So you want to test this level? Yeah. Okay. Is that helping? Yeah. Is that right? Yeah. Yeah. Okay.
But I think it's what yeah.
Yeah, you get one.
Mm. Things I did think I had 45 minutes, and then I noticed I only have 25, so it's going to be a bit of editing on the fly.
Start the session.
Shall I start? Excellent. Okay, thank you. Good morning, everyone. Thank you very much indeed for inviting me along. It's a great pleasure and an honour to be here. My name is Andrew Katz. I have two hats. I am a lawyer, and I've been advising on open technologies for around 30 years. And I also run a company called Orcro, which specialises in open source software compliance. So today I'm going to be talking a little bit about open hardware, open source hardware. The terms are sort of largely interchangeable. But to give you a little bit of background, typically we're talking about licensing a design, and that design will be licensed under terms that, if you're involved with open technologies, open source, free software at all, will be very familiar to you. So the license must allow making that design, modifying the design, and redistributing the design with or without modifications. None of that will come as a surprise at all. And there's an organization called the Open Source Hardware Association. They have a definition, and that preamble, which is on the screen there, looks very similar to the definition of free software. So just to put things in context, what are we talking about when we're talking about open hardware? Typically people tend to think about electronics. They can also be thinking about silicon chips, but they can be thinking about more physical things like cases, racks, and furniture. Typically mechanical devices can also be considered as being open hardware. So I've been involved in projects involving open source hardware, cars, boats, for example. All of these are items that can be released under open hardware licenses. And also 3D artistic works as well. So they don't need to be functional, they can be purely aesthetic. I put 3D printed works in there because people often think about 3D printed works as being a typical classical form of open hardware. And interestingly enough, fluids can also be open hardware as well. So for example, if you are releasing an engine, a car engine, something like that, it's going to need oil. Maybe you'll have a special formulation of the oil that it requires. And that can also be open hardware as well. Now, we have a number of intellectual property challenges when it comes to licensing open hardware. Now, I mean, typically, we'd be looking at copyrights, and in that case, that's something that people will be very familiar with in terms of open source software. Patents tend to impinge more on hardware than they do in software. In many jurisdictions, it's not possible to patent software as such. So patents tend to impinge more often on hardware than they do on software. There are any number of different sorts of design rights in different jurisdictions which can also apply. There are strange individual sorts of intellectual property, like plant breeders' rights in some jurisdictions as well. There's also semiconductor topography or mask rights, and which are more likely to be the sort of thing that is covered by open hardware licensing. There's database rights as well. So there's a whole plethora of different sorts of intellectual property rights which can be covered, which can apply to open hardware. And broadly, there are two types of open hardware license, analogously with open source software. So there are permissive licenses that essentially allow you to do anything that you like with the design. And then there's reciprocal or copyleft licenses that require you to make the design documents or the modified design documents available as well. So again, if you're familiar with open source software, you'll be very familiar with this as a concept. So the sort of challenges that we have when we are trying to come up with an open hardware license is that you will find that there is a more complex mix of intellectual property involved in open hardware than there is in open source software. So all of these aspects need to be considered in the license. One of the less understood situations, as far as software is concerned, there are many, many chances to allow the license obligations to impinge. So essentially, every time you make use of that software, every time you transfer it, if you're going to be downloading it, installing it, running, etc., copies of the software are going to be made. And every time a copy is made, it's going to require a license for that particular use case. And whenever a license is required, then it means that the conditions that apply to that license will also apply as well. With hardware, that's not necessarily the case. The intellectual property obligations are not going to impinge as often. I mean, for example, if you make a 3D printed hammer, you don't need to rely on any form of license every single time you use that hammer. And the sort of conditions that we're talking about, again, analogously with open source software, are for permissive licenses. You're looking at things like attributions, license texts, etc. And then for reciprocal, share alike, or copyleft type licenses, you'll also be looking at making the source code available as well under the same license. So just to give you a brief idea of the sort of spectrum of open hardware licenses that are out there, a lot of people just use open source software licenses. That comes with its own sort of particular problems, but you'll frequently see open hardware licensed under BSD, MIT, Apache, and some new license called the GPL, which I think is supposed to say GPL. And quite frequently you'll see the designs also licensed under content licenses, which are typically more appropriate for content, such as the Creative Commons suite of licenses. And then there are a number of licenses that have been drafted specifically for use with open hardware. CERN Open Hardware License, the SolderPad hardware license, TAPA, the Open Compute project licenses, which I would have a sort of slight query as to whether they count as open or not, but that's probably not something to discuss today. And most recently, the Open Atom Foundation in China has just released the Open Atom Open Hardware License, which is a permissive style of license. So this raises a number of questions that you need to bear in mind when you are drafting an open hardware license. So what level of detail do you actually need in the design? Now, one way of thinking about this little sort of tool for thinking is to think about what is software made of. Well, software is essentially made from a pile of zeros and ones. What you're doing is you are coming up with a recipe for combining those zeros and ones in a particular order, and you will end up with a piece of software. Hardware is different. Hardware is made of atoms. Atoms are not quite so predictable. So when you're compiling software, you are going to get this relatively predictable string of zeros and ones. I like to say that software compilation is deterministic. Computer scientists will tell me that it's not, because there are plenty of variables depending on the compilation environment. But let's assume, for the sake of argument, that it is. And certainly, it's possible to come up with mechanisms that allow builds to be reproducible in certain ways. So same output means that same input means that you have the same output in each case. That's not necessarily the case with hardware, because you are not getting a set of instructions that will enable you to make your piece of hardware out of a pile of atoms. You're necessarily going to have some level of abstraction that is higher than that. And you will necessarily be looking at components there. So for electronic circuits, if you're looking for a design of an electronic circuit, that design will be made out of components. It'll be made out of resistors, capacitors, inductors, transistors, and so on, as well as the printed circuit board that they are connected to. One thing that I'd like you to think about is just moving to a different realm of openness now. If we're thinking about things like open government data and open source artificial intelligence, then they are also essentially made of components as well. The training data can be regarded as a component as far as AI is concerned. If you're looking at government data, then even though that be available under an open license, what you're getting is you're getting a bunch of statistics which you are able to use and reproduce and so on under that license. But what you will not be getting is the fundamental data that created those statistics in the first place, the outputs from the censuses or the surveys or whatever the government has undertaken to provide that information. So this question of how to deal with components in open licensing, it is not a new one. It's been considered in other fields such as open data licensing and open artificial intelligence. So just looking at the question of components, if you have a design of something that contains components, do you also need the instructions to make the components individually? So we're looking at a sort of hierarchical structure here, where you have a design contains the components. If that design is to be regarded as open, do you need the instructions for how to make each one of those components? If you don't have those, can you truly describe the design as open? And when we drafted the CERN Open Hardware License, we came up with a concept of available components. And if a component is available, that means that either you do have all the instructions to enable you to make it, or alternatively, you have information about where to source that component and all of the specifications that you will need in order to make use of that component in that particular design. Now, just briefly looking at the Open Source Hardware Association definition. As well as talking about licensing, and clearly the design would have to be made available under an open license, it also has to fulfill some additional criteria. First of all, the design has to be made public itself. That seems relatively obvious, but at least that's explicitly stated in the Open Source Hardware Association definition. But the definition also states that the interfaces to software must be made public, or the software must be released under an OSI approved license. And if you have a hardware design and you want it to be certified by the Open Source Hardware Association, they have a certification program, then some additional requirements are that you must use open components wherever possible. So that's not an absolute requirement, but it's a wherever possible requirement. So this demonstrates that these are requirements that are over and above the simple requirement that the design itself has to be made available under this license. So let's look at some issues with openness as far as sharing and facilitating reuse are concerned in licensing. So I'm going to quickly cover a few topics here. I'm going to compare the open source hardware development process with the open source software development process. And then we're going to look at whether that process varies depending on the type of hardware that we're talking about. Because some hardware projects are very much more like software in the way that they're designed, developed, tested, implemented, and so on. I'm going to very briefly look at some economic arguments that will distinguish between open hardware and open source software, particularly as far as copyleft is concerned. And then I'm going to look at some issues that are specific to permissive or copyleft licenses in particular. So let's ask ourselves the question, why is open source software so successful? And we've very much focused on the licensing model. And the licensing model is undoubtedly an extremely important factor here, but it is not the only factor in the success of open source software. One of the factors is the development environment is free or low cost, and it's very easily available. And for typical piece of software development, you can actually do that development on some pretty low cost hardware as well. Much of the software and tooling that you need is going to be free or low cost. So, you know, you can use Linux as your operating system. Your development tools like GCC, also free and low cost. And critically, the platforms that you will be using in order to collaborate and track that development are also easily available and accessible. And in many cases, they're free for open source projects as well. So if you look at GitHub and GitLab as classic examples of that. And then, of course, in order to make use of those platforms, you're going to need internet bandwidth. And that is now available at reasonable cost to most people in most parts of the world. So that creates a virtuous circle of easy community development, and it means that many developers are potentially available to help and to create a community of development. And that community can be very broad, I mean, potentially worldwide. So how do we contrast that with hardware? Well, it can require expensive proprietary development software. So if you think about sort of CAD/CAM systems, for example, those can be extremely expensive. In order to make hardware, you know, the harder sorts of hardware, you're going to need complex and expensive physical tools, things like lathes and milling machines, 3D printers. In order to ship hardware, they're physical items, so there's shipping and transport to consider. You may need a particular amount of space and environment in order to create that, and maybe environmental constraints. So, you know, if you're making silicon chips, as an extreme example, you're going to need an extremely clean facility. It's going to have to be temperature and pressure controlled, humidity controlled, and so on. And then, of course, you'll be thinking about the cost and the quality of the feedstock and the components that you're using, the raw materials that you're using to create that hardware. So let's have a look at the design, build, test cycle. So this is applicable to software and hardware. So you basically start with a design, then you will build that design as part of the build process, then you'll test it, and then you'll go around that cycle, round and round and round, until you feel that you're in a position to make the product available, and then you'll go to the productize section, and the customer gets access to it. This can be as simple as just making the code available for download somewhere, or in the case of something physical, it can be significantly more complex than that. But then that will always go back to the test cycle, and that will go round and round and round. And the distinction between hardware and software is that whether these activities are happening in the physical domain or whether they're happening in the digital domain. Because with software, if everything's happening in the digital domain, this is a lot more effective, it's a lot quicker, it enables collaboration much more effectively. If it's happening in the physical domain, then the build, test, design cycle will slow down significantly. Collaboration becomes much more difficult. Now, this can be short-circuited to a degree by adding simulate in there as well, and this happens a lot in terms of hardware. You know, car manufacturers have a lot of extremely expensive software that will enable them to simulate various designs, And that will certainly reduce the cost. But again, it's expensive software. It's not necessarily accessible to individuals. So this is something that creates another difference between hardware and software. So let's look at one particular sort of open source hardware development, which is the FPGA, the field programmable gate array. So if you're not familiar with an FPGA, it is a silicon chip that enables itself to be, you can configure it in order to essentially become any other sort of chip. It can become a processor, it can become a piece of memory, it can become some form of interface or whatever. And to do that, you write a formal description of the logic in a form of hardware description language, and then you use that logic description to create a bit stream, and that bit stream is literally just a sequence of zeros and ones, which you then apply to the FPGA, and once the FPGA has been configured using that bit stream, it becomes whatever you want it to be, whatever you designed it to be, the memory chip, the interface, the UART, whatever that happens to be. Now, with software, obviously you write code in a programming language, and then you compile it to create object code, and you can run that on a computer. This is very similar. The process is very similar, and in fact, a hardware description language looks very much like a software programming language. And actually, if you speak to HDL developers, they'll often talk about the code they're creating as code, and they will talk about, rather than configuring the FPGA, as configuration. So it's a lot like software development. So HDL development has a lot in common with software development. And from that perspective, a lot of the dynamics that apply to open hardware development, if we're talking about HDL development, they are very similar to the dynamics that apply to software as well. Right, I'm not going to go into this in detail now, but there are issues with enabling reciprocity and copyleft to apply to open hardware, because, as I mentioned before, there's less opportunity for these obligations to apply with open hardware than there is with open source software. There's also a problem with copyleft, in that it's difficult to figure out where the boundary for the copyleft should lie. So if you have one component that is in your piece of open hardware that is subject to copyleft license, does that mean that, for example, the whole of whatever that design is that contains that single copyleft component also has to be released under the same license? So this is something that can be quite difficult to deal with. And an economic argument is that around reverse engineering. It's often a lot easier and cheaper to reverse engineer and to recreate something in the hardware world than it is in the software world. So I shall skip this one. This is the economic issue here, is that basically with software it costs close to zero to make a copy of even incredibly complex software. It's just a question of copying the bits. With hardware, it's much more difficult. So if you're going through that process anyway with hardware, then you're already committed to a large amount of expense. Essentially, it's fairly easy to avoid copyleft licensing of hardware, because reverse engineering and essentially creating a sort of clean room mechanism for redesigning the hardware is significantly more straightforward than with hardware than it is with software. That's an oversimplification, but it's one of the pointers as to why copyleft license may not work. So what we're looking at here is a sort of form of hardware in a spectrum. Essentially, a lot of the criteria that apply to open source software, and the reason why it's so successful, I maintain, are much more likely to apply to open hardware if that open hardware has software-like development characteristics, such as with an FPGA. I call it a hardware in a spectrum. I think it's a dreadful piece of terminology, so if you can think of something better, please let me know. I was involved in the European Commission impact study on the competitors of hardware a few years ago, open source software and hardware, but I was leading the hardware side of things. We do go into some of this analysis here. There's a link on the screen there for that, and I'll share the slides. But if you want to see some of this analysis in greater depth, that's there. And we took some of this thinking into the CERN OHL. So what can open hardware learn from open source software? Well, there's an example of many of the activities that are very successful in open source software that can also apply to open hardware. And again, I'm not going to go through those individually. So in summary, open hardware is more challenging than software. But you've got to be aware that the community and development dynamics may well be very different, and do not assume that other opens will work like open source software. We have some advantages in open hardware. There's less license proliferation, but beware that copyleft and reciprocity may not work as well for open hardware. But none of that means that open source software and open hardware aren't fields that can learn from each other. Right, thank you very much indeed. Thank you. I don't know if we've got time for any questions.
Okay, thank you for that overview. So you mentioned that it's difficult to determine where the boundaries are specifically with regards to reciprocity.
Yeah.
Why is that difficult? Like, it seems to me, like, intuitively. So if you have a piece of hardware, like a circuit that is licensed, let's say, certain hardware copyleft.
Yeah.
And you use that piece of circuit is reused in a larger schematic.
Yes.
That, to me, means that the entire thing should be copyleft. But that's the point.
Okay, so I mean, if you have a resistor that's copyleft, then any license that any hardware that contains that resistor is therefore going to have to be released under that copyleft license. And then when and let's say that resistor goes onto motherboard, as soon as you put the motherboard into a case, does that case then have to be released under the open hardware license? And then when you put that case into a rack, does the rack have to be released under the open hardware license? So I think this is the issue that we have is, where does it stop? What is a component? And
this is similar to like with software where you have, if you put a piece of GPL software in a proprietary operating system,
yes,
it doesn't mean the entire operating system is GPL.
Well, it might. And this is something that we spent a lot of time sort of analyzing and looking at. Certainly, that's not the case if it's LGPL. With GPL, it'll depend on the interaction between that piece of GPL code and everything else. And this is something that's fairly well understood, and still not completely understood, but fairly well understood as far as software is concerned. But in my view, it's not quite so clear cut in hardware. And I think it's also in a way becoming less clear cut in software as well, because when you're looking at technologies like containerization, for example, that tends to make it quite a lot more difficult to analyze exactly where these boundaries lie. Yeah, thank you. Thank you for the question.
How about opinion about data sheets?
Data sheets. So I think data sheets are critical. I mean, certainly thinking from a sort of open, a CERN open hardware license perspective, in order for a component to be considered to be an available component, it will have to come with a data sheet, and that data sheet will have to provide all of the information that's necessary to make use of that particular component. And it's sort of obvious things like if it's a resistor, the capacity, the power capacity of the resistor, the resistance, but also things like the physical size and shape of it. And it could also, in certain cases, also require certain sort of tests and calibration suites and so on that come with it as well. So what's specifically required in the data sheet is actually going to depend on what the ultimate use is, what the use case for that particular component is going to be.
Hello. Thank you very much. Well, I have a question about patents and this licensing.
Yeah.
Yeah, I have some, for example, some piece of hardware, and I patent.
Yeah.
This patent is basically, let's say, restriction on others to fabricate my device in exchange of making the design public, right?
Yes, yes.
So once I have that, for example, then I kind of like open license it with these licenses, and that will allow people to fabricate my device.
Yeah.
So far, so good.
Yeah.
But for example, if I have a device that for some reason cannot be patented,
Yeah.
then does it make sense that I open license it?
So you'll.
You get the question, right?
Yeah, exactly. So what you've just described is the way that the TAPA open hardware license works, or doesn't, as the case may be, which sort of makes the assumption that all hardware might be patentable or not, and its obligations rely on the fact that it might be patentable. But of course, I mean, there are plenty of other intellectual property rights that will apply in a design that are not necessarily patents, which can still be licensed and can still be used to apply conditions. So copyright is the obvious one, but it could also be database right in a list of all the components, for example. So from that perspective, there's not a huge amount of difference between open source software and open hardware, but there's probably less focus on copyright in open hardware than there is in open source software.
In the case of hardware, the copyright in the physical thing doesn't apply, right? Because copyright applies to intellectual property rather than.
Yeah, I mean, this is yes, that's a good question, and this is something that varies a lot from jurisdiction to jurisdiction. So some jurisdictions will say the copyright only applies to the design itself, and as soon as you turn that into the hardware, then the copyright becomes irrelevant. And in that case, there's not going to be any restriction on somebody taking just the hardware, reversing reverse engineering that piece of hardware and then replicating it. In other jurisdictions, you will find that the intellectual property, the copyright, will carry on into the design. So, an example of that would be a circuit board layout, which is, certainly under English law is regarded as being an artistic work. And it's still an artistic work when you take it from the design phase and put it onto a circuit that's etched in copper. So that will vary a lot from one jurisdiction to another.
Okay. For example, for patenting something you demand, maybe some lawyers could be. But if I don't have it and I just have my piece of software as a hardware and open licensing, would that somehow protect my design if someone wants to patent my design?
Yeah, again, this varies a lot from jurisdiction to jurisdiction and also from the type of intellectual property. So copyright happens automatically and you don't need to register that, although you can in some jurisdictions get advantages by doing that. Patents will always need to be registered and they're very expensive to do that. As a hybrid, there are forms of design rights. Some of them happen automatically, some of them don't. So database rights in the European Union happens automatically. It varies a lot from the type of intellectual property and also from the jurisdiction that you're looking at as well. Yeah.
Thank you. Thank you.
Do we have any more questions? Then I think there's a short mini break. There's some seconds that we'll take and we'll resume at the next half hour.
Right, thank you very much, everyone.
Presentations, by the way.
Just give me some, any stuff here. So, can we can we on this? Am I switching this? Sorry. Here, and test this one, and I will on the 3-day conversation. Thank you. Next, yeah. Yeah. Okay, thank you very much. That's it. Thank you. So my sister, if you try people's my business partner will translate.
Yeah.
Thank you. Any else? All right, so, no, not. Yeah, I just want. Yeah, just like that. Sorry, so may I check my uh, my laptop to demonstrate and
After you finish the presentation,
yeah, after the file presentation, so yeah,
you will unplug to
plug yeah,
unplug and
yeah,
plug it.
yeah,
Will you check it out?
yeah,
Yeah,
just, how is it many people using this laptop? So on the-
After
yeah. Yeah.
So, okay. Okay, thank you.
This is the pointer.
Ah, okay. Ah, okay. Ah, sorry, I need to check some my presentation about the script, my script.
Oh, okay.
I studied, I'm 10 to 45.
Okay, okay.
Sorry for a second, please. And the session is kindly and our partner will be translating in Thai. So if you Chinese or my business partner will translate, kindly translate my session. Please come here. So you don't know, please. 戻ってこうかよ。よいしょ。
Hello.
Is the time. I was wondering.
Testing one, two. Hello.
I have thought not only. Sorry. I don't but also in a very country as well. And I also did event in Taipei, talking about automotive readiness. I will automotive things for readiness, and you can use the Raspberry on I use the base for readiness. And this is years ago picture. I have looked at the makeup machine then, and as the event, and there were the committee leader, and since I makeup machine then, I have thought, to the question talking about my project and integrating Raspberry Pi audio project. First, I will introduce again the Raspberry Pi and the Pi update. Because your Raspberry Pi 550 gigabyte Pi have released on this early this year on 9th January. What is the difference on the product? And from a product 8 gigabyte type, 4 gigabyte type, or the 8 gigabyte type. And it is good for the release for the new CPU updates. And the former CPUs are 2712 type in the constant on the unused version. And unused for associate area. So Raspberry and Broadcom discussed with the unlimited areas on the to omit it. So it used to be all CPU used to be killed by unused area. And now they don't have to care about if unused area and so on. I will demonstrate the difference on the scissors and the two 712 CPU with the two 712 different set and the difference is you can click on the command and the difference in the CPU. I will go to the later you can see on the VPU unit and if you check all CPU is small and basically I you can see the CPU QPU command. Now, well, it is good. Here, you can see the CPU set P1 CPU, the result is QPU is 15. Sorry, 16. And TMU is right in the 4. What difference the QPU is and the Q by how we calculate what the CPU value. And I will demonstrate later about the Q with data flow about the UR code later. So this is good news for the COVID. Our parent chip based on the Raspberry Pi Pico. XGP based on the Raspberry Pi Pico. Now, it first released on some the controller is closed. But now it is open. You can see GitHub about this the hardware thing, which definitely can be done. But people you can program to I/O the whole like the Raspberry people you can program it the I/O on the Raspberry Pi and 500. So please check the GitHub this year. Fairly now open. And Raspberry people now they supported in good form and supported Raspberry good form on the Ubuntu on the and harmonious also and support and equal with Raspberry Pi and 500. Sorry. And now and check and so you can see that for the and Raspberry Pi and so VMI and it is included by soldering or something and based on Sony technology. And now Raspberry Pi and Raspberry product is all made in UK and the Sony paper. And now improving quality of the product with Sony technology. And so you can use active cooler and the good in OS, but you do you can see it's cooler and working the Ubuntu or the Android, but it doesn't work all on the program because it's slowly down to the firmware things. So you see once I read so you have to see OS on the Raspberry Pi, it stops. But you see the Ubuntu on the Android the phone is always working. So because it is well also it is well the request neither with Sony and family. So it is safe and proprietary protocol. So it is partly works on the Android active program. So now is a better way to group system in SD card. Sorry, SD card or HDMI or some USB boot or other kind. And well, some of people so they wondering the SD card is useful. And now Raspberry and the 5 or little and it's too much chewing support on the Raspberry Pi or little. If you go on the theory on the SD card is not efficient for using on the Raspberry Pi product, and you're well on the it's rapidly counting in the SD card application a bit. So you're Raspberry sorry, the SD card is not efficient. So but even now still improving the SD card using if you use the S
sticker, and you can try every one too, in the sticker. And you the sticker and also now using for the delivery, and you see from their federal customer products and using on the delivery system. And it's only one for it's not only one for the sticker, but also even some of them and create two put stickers which which can use on the every t-shirt how supported on the product. Over there. And we are very much nervous that you bring on this power supply system because it is something never saw it using by on the power supply usage. It's 5 volt amperes to the 5 volt 5 ampere system, which the unit so it's recommended to 7 watt, 27 watt is part of the system. So does it like do not recommend such as for the but for charging system, which you are uncle some of the progress, because it works good, but some products they cannot use on the Raspberry system because they check the file by probably the file putting on the PD communication, and some doesn't work on their own the PD communication in the file display. I will also demonstrate it. And next thing for even the unit that series only now only this is my update on same file, not same file. So now probably file update and minor update. Let's say you come here and it's free-based product, but CPU changes on the CPUs and the computer module 4S and the third port programmed by computer module 3. And the same for even now on the these on the engine oxide, which it is patient on the temperature on what. And here you take suggestions for different techniques for video users. You see in the 500, you can see the boots on the anonymous, it works on the good and on the Linux, and it's useful, and if you feel noisy on the PWM cooler, and it's very improving. It's very improving on the performance. It's a keyboard, and there's heat sink cooler, not using a computing pump, and improving it for the cooling system, rather than computing with rather by only 5 or 5 products. And it is a bit faster than Raspberry Pi products. So if you're computer programming and the clients like the QPU for AI and so everything, it may be better to using another type of hardware. If we using if you use something like benchmark, it is a big difference than another type of hardware. So my members so I'm using another type of 2W only. So members the try for this project use something like Spanish and the Japanese English line. And so I would like to introduce even the favorite project issue P on the use and the now porting of the basic OS on the Raspberry Pi 4 product. And it was good on the Raspberry Pi and the phone. And now trying to work on the Raspberry Pi computer and and it has the correct memory and responsive than all the rather than but I cannot say what in the sorry and the other so I would introduce after one major partners and the concern is that kindly and the kindly and continues for the different I'm sorry.
Hello, everyone. So basically, we are the Raspberry Pi authorized reseller in Thailand. So she's my application manager. Is there any Thai people here that require translation? So she can help to do the slide translation for you. Is there any Thai? Do you need, do we still have time for translation? 3 minutes. Okay. After the event, yeah. We have a table there with the Raspberry Pi 500. Yeah, you can help me. Thank you very much.
So thank you very much. So I will see and you can talk to the background and so if you are in Thailand and they can bring and introduce the other product. If you can see other side. So thank you very much for and see you next in the podcast if you going to if you with someone in the August and the folder my and presentation and my Japanese truck and see you in Taiwan. And thank you very much. For me, I will do demonstration for you. I will demonstrate. So I will demonstrate the fact that I will come for you. Sorry for that. Thank you very much. Thank you. Thank you. And it is how long?
Then I will just I'll do it, no? Yeah.
Yes.
Let's do 1, 2, 3.
Yes, please.
Yes, and then
It's okay to
tiếp về nhà. Xem nó bị tay chịu. Yes, no USB.
USB-C, but if you want a converter, I have one.
Okay.
If you could, yeah. This can go sit on the floor. Oh, converter. Yeah. Okay. Where does that work? Like the multi one. Yeah. Super helpful. Yeah. Hey, good to see you.
Separate room.
I know, right? I wish I had found you. I'll let him do an actual thing, but.
No, just searching into conversations, right? Yeah, conversation.
This is the last
name?
session.
I will.
Thank you very much.
Thank you. Happy
VRC.
Oh, VR. Two, room 3.
Okay, maybe we'll set up.
Yeah.
Okay.
Can I put the slides onto this?
Yeah.
Okay. Can I use a different browser?
Yeah.
Okay. You're sharing the entire desktop?
Yeah. Sharing the internet also. Whatever you're very.
Ooh.
Yeah.
So if I make this
Yeah.
working.
Yeah. You can slide. So can I choose your mic?
Thank you very much. Wow, we got lots of people. This is very nice. The session is slightly scheduled for a little bit longer. Does this work?
Yes.
Okay. The session is scheduled for a little bit longer than I need. So we've got a little bit of time to do more hands-on activities afterwards. So what I'd like to do is show you some background context, mostly just pictures, so you don't have to stare at my face all the time. I'll walk you through the context, and then later on we'll do a little bit of hands-on, depending on what you're in the mood for. Okay. So we might not be here for the full time schedule that the slot is allocated for. So if you not interested in hands-on, feel free to leave anytime. With that, thank you for joining. Thank you for attending. My name is Saad, based in Singapore. I'm a tech person, but during weekends I do something a little bit more meaningful, in my opinion. I run a small nonprofit that invites tech people to come and contribute their skills and knowledge and expertise and time and effort towards solving for persons with disabilities. And the group is called Salvage Garden, and that's a bit of a dated reference if somebody's familiar with an Australian pop band. Some heads are nodding, which is great. It's a community started, community-led group. We sort of came together during COVID to try and solve the needs of people who were being left behind. And in Singapore, we found that the need was people needed appropriate devices at home that maybe they didn't have access to otherwise. So building on that, Salvage Garden was a group of volunteers that came together and recognized this need. They felt that, you know, the skills that they have can be put to a little bit more of a meaningful purpose. And I'm pretty sure everybody in the room has had some experience with this. And if you haven't, this is a very good place to start. So the Braille Wrap is a device that I want to talk about. It's an open source Braille printing machine. Who here is familiar with open source? Excellent. Who's familiar with Braille? Very nice. So some experience, you know, you don't have to be an expert with this, but the fact that you know what it is already a good place to start. So for those who are not familiar, this is Braille, printed on paper. It's designed to be a non-visual communication language. Does anybody know where it started? The word Braille, where it comes from? Yes? Yes. Who was French? But do you know how old he was when he invented this? Yeah, he's about your age. How old are you? Exactly your age. So if a 17-year-old can come up with a language that is completely unique, I think it's up to us to see how we might be able to take our skills and apply it towards this kind of end. So this was a long time ago. The technology at the time was very different. It was sort of hindered by the limitations of what was industrially available at the time. So, but the way that Braille was made back then has pretty much remained the same. There are ways where you can just do it by hand, use a little pokey device and a stencil, and you're able to write Braille by just making dots. But the machines have not really evolved. There's a lot of need for innovation and input in this space. There are very few people doing interesting things. So the device that I want to show you can do a little bit more than the traditional Braille. Mostly the standard talks about text. So here you can see some examples of more than text. That's a recognizable symbol, I think. I hope. Yes, okay. Next to it, you have these things. So this is the text. And we don't really know because we're using our eyes to try and read something that is meant for closing your eyes. So really, if you want to read this, you have to be able to do it in a way that is not using your eyes. So it's important to recognize that when you see this, it looks weird because you're seeing it. You're supposed to be feeling it. So that's why the language looks a little bit strange. So it's a little bit weird when you see like people's name cards with just dots printed on it without it being raised. I know that's like a positive trend, but it kind of defeats the purpose. So what did I want to say about this? Yeah, the machines that I'm talking about can do a little bit more than just text. Most of the Braille machines that are available have been designed to print one alphabet at a time. And each alphabet is a combination of grid patterns. So you can see that there's 3 rows of dots and usually 2 columns. So that's the 6-dot method. There's also an 8-dot pattern. So the machines that were designed in before digital times, you had, they would print one alphabet at a time, depending on what pattern it was. And they were very good at what they did in the sense that they would produce large quantities very quickly. And that serves the industrial sort of mindset of producing Braille content. But in our case, the machine that I'm going to demonstrate later on is able to do 1 page at a time. So this is an A4 size sheet. It goes into the thing, and it prints only 1 page at one time. That slows things down, yes, but it opens up the possibilities of doing a lot more with what you're seeing on the screen. So if you're printing like line by line, you're not limited to text. You can also do images. Make sense? All right. Who's familiar with the RepRap 3D printing? Excellent. Has anybody made a 3D printer? Yes, sort of. That qualifies. Yes. Was it? Yes. Okay. We've got 2 people who've had experience building a device, which is great. Assembling a printer is a good way to understand how it works, and that I think will be helpful when you try and take a look at how this thing operates. So the very first printer, the grandfather, the granddaddy of all 3D printers, was the RepRap. Who recognizes the RepRap? Seen this before? Yes? Was it on a Wikipedia article? Yes, exactly. So this picture is taken from 2006. It's on Wikipedia. This was the very first demonstration of how you can invent a machine that is able to produce another machine using the machine that you just designed. So that's the concept behind the replicate rapid RepRap of 3D printers. That's kind of where 3D printing came from. Now we kind of like take it for granted because you just buy the thing, plug it in, turn it on, and then it prints stuff. But the starting point of this was, how might we design a machine that is able to print most of the parts that are necessary to make another one just like it? So it goes all the way back to the design. So if you look at the Wikipedia article, you'll see back in 2006, we talk about this thing cost $10,000 to develop and to design. That was the first one. So we call that the parent. And then using the parent, the $10,000 device, you're able to manufacture the child, which costs 10 times less. Or now you can get one for $500. So back in 2005, 2006, now we're in 2025. You can see how things have changed and improved. There are a lot of different types of 3D printers that have come out. The Prusa is very popular. Bamboo Labs is being the new generation, is flooding the market. So these things are a lot more affordable and accessible, but they all sort of trace their origins back to this family of wrap. And that's actually where we get the name Braille wrap. So the wrap part is because it's using exactly the same software that the original wrap used. So later on, I'll show you a little bit more about the parts of the device, but you can see here the electronics, the brain of it, runs on an Arduino. And that's the same microcontroller that's used for the wrap, both the parent and the child. The software that operates and moves all the machine parts inside is exactly the same software that runs on this. It runs Marlin. Has anybody tried Marlin before? Oh, wow. Okay, that's unexpected. That's very good. We've kind of moved on from Marlin to other flavors of software that runs on the thing, but it is properly open source. So you can go in, fiddle with it. The thing I would recommend doing is going and changing the name of the printer. That's the easiest thing to do. So you can just change the Marlin, the name of the printer to Braille wrap, and you're good to go. Okay. This is a FOSSASIA presentation, so I had to throw in a chart. And this is kind of like, showing you the evolution of different 3D printers. So you go all the way back to the original wrap back in 2007. It feels like a long time ago, but if you look at where the Prusa is, it traces its origins back to an open source project. Okay. The context in which I'll be presenting this device is how to make one with your own community. Because it's an open source project, it's not my design. It was started a long time ago by mostly, I think, a team of tech people based in France. And they are the ones who are maintaining braillewrap.org, which is the sort of starting point for most of the resources you need to get started. So I've had the privilege to take this machine and the concept of the machine and implement it in 3 different locations. So I want to show you what I've learned from that exercise. So if you are interested in building one of these in your own contexts, you'll know what to look out for. Has anybody been to Bhutan before? No? Does anybody know somebody who's been to Bhutan before? Excellent. Okay, this is good. It is very picturesque, and they call it the Shangri-La, and there's a good reason for that. I thought it was mostly just tourism marketing and so on. When I went there, it's all true. It is a special spiritual kind of place, and I strongly recommend if you have the opportunity to go, please go and visit. It is amazing. It looks like a postcard picture that I got from iStock Photo, but this is a photo I took. Everything just looks like this. It's stunning, amazing. So I strongly recommend going and visiting. But the thing that I wanted to point out is there's very few people who've been there. And the closest we can do is probably find somebody who's already been there or is from there. And the reason for that is the country is isolated. It's hard to get to. It's hard to send stuff to Bhutan. And so if you think about what it is like to live in that country, yes, it is spiritual and beautiful, but getting stuff into the country is incredibly difficult. So for us, we sort of take it for granted. We just, go online, do the shopping, comes from China, it shows up in a few days. We complain about the shipping costs and the shipping time, even though it takes just a couple of days to show up. But in Bhutan, that couple of days is usually forever. The shipping option do not exist. And if there is shipping, it tends to cost a lot of money, and it takes a lot of time, and it's highly unreliable. So being a remote mountainous country like that, not really having access to the supply chain network that we all take for granted is a unique situation for something that can be manufactured locally. So if you have a 3D printer, you don't need to go and get it from, get something made in a factory. So having access to a 3D printer allows you to make something locally. And that's something we capitalized on during my time at in Bhutan. So I worked with College of Science and Technology. So a small group of students who are based in a city that's not the capital. So I've put 3 stars up. And you can see the star at the bottom is near the border to a different country, which is India, where I'm actually from. And so a lot of the supply chain comes from the neighboring country, which is India. And there's a large dependency on equipment and goods coming over the border. Often people just walk across or drive across. So the place where the college is placed is at the border, which is different from the 2 stars on top, which is where the capital is and the airport. So there's only one airport in all of Bhutan, and it's the most dangerous airport in the world. You can't see the place where you're landing. You have to sort of go around the mountain and then land. It's super weird. There's only like 14 pilots qualified to land on that airport. So if one of them falls sick, no flight. But these are the people that I was working with. It's a nice group of internationals. All sorts of people from different countries came together. The context was the Fab Lab conference, which happens every year. This one was hosted by the College of Science and Technology. So it was a collaboration between 3 different groups of people. The Fab Lab Network, the College of Science and Technology, and a team from Japan who were already there setting up their makerspace. The Fab Lab. So this is what it looked like when we went over the challenge. We only had 5 days in which to start building a device from scratch. So what I requested was whoever was participating in this, they would bring in whatever resources they had from whatever countries they were coming from. And this was a good idea, it turns out, because again, like I said, shipping stuff to Bhutan is difficult. So we got a whole bunch of Arduinos, ramps boards, stepper motors, rods, bearings, belts, and the rest of it we were able to print in their Fab Lab. So we had the facility to do laser cutting over there, and we had the facility to do like 3D printing over there. So everything that could be done within their lab, we did there. Everything else that couldn't, we just brought along in our luggage. So it was quite easy to do, mostly because everything that you need is already listed on a website somewhere. So people knew what to bring. And if you have extras of something that costs less, it's okay. You can always repurpose it, reprogram it, and use it for something else. So it basically needs a mindset. And that's actually what we were able to do with the students. We were able to transfer this idea of being a hacker, being able to think out of the box, being able to reprogram and repurpose what you have access to. And so you make the most of the resources that are available to you where you are. So I don't know how it is in Bangkok, but if you are to go out and buy an Arduino, does anybody know where to go? Yes? There is a physical store. You can go in and buy an Arduino from a shelf? Okay, so that you have electronic stores. Lots of them?
Yeah. It's a puzzle to find it, but it exists.
Okay.
Yeah.
That's good to know. And it's similar with Singapore as well. There are physical places where they have them on the shelf. They cost a little bit more than buying them online, but you know that it's there if you need it. With Bhutan, it was mostly construction material. So the kind of electronics that you would get are mostly used for infrastructure development or manufacturing. So that scale of supply, the kind of supply things we had access to were for that kind of industry. The thing that we found useful was, like screws and nuts and bolts and so on, but also was a bit of a discovery that is their version of WD-40. And if you've ever been a maker, without WD-40, there's no point getting started. We also use this as an opportunity to explore a little bit more out of the box. What I found out was because they are bordering India, and there's a sort of like an active trade that happens across that border. If you just walk out of the College of Science and Technology and head towards the border, in about 45 minutes, you'll be able to walk across to another country. But at the border, they have a whole bunch of businesses that are doing secondhand stuff. And we found a shop that was stockpiling old ICT equipment. You probably recognize the scanners. Has anybody used the scanner recently? When we take pictures of everything now, we don't need a scanner. But these devices have the sort of rods that we need in order to make one of these devices. So you don't have to go and find new things. Because we are working with something that is open source and highly flexible, we can adapt the design of the machine to fit whatever parts we have access to. And that's a distinct advantage of anything that's open source in the hardware world. We take it for granted with the software. If it doesn't quite adapt, we just write the bits and pieces and then we make it work. But when it comes to hardware, it's a little bit harder. Hardware is hard. So the box there was to keep only what we thought might be useful, and all the other, like the plastic bits that were proprietary or designed to only work with that thing, we got rid of. So they went back to the e-waste place. But the guy who we spoke to, he was like, yeah, you can have as many as you like. So we got all of that stuff for free. So the context in which we were working was, again, a distinct advantage. I have a small little video to give you a sense of what the space looks and feels like. So if this loads, you'll be able to see, to get a sense of what their space is. It's a fab lab like most other fab labs are, but you don't have to have a lot of complex equipment. So this is sort of like a virtual tour, if you like. So these are the students I was working with, and they were trying to assemble this without reading the instructions. It was so much fun to watch them figure it out, and they did. They figured it out. I printed out all the instructions that were available online, but the first step they wanted to do was try and put it all together themselves, which is amazing. What I also want to show you is what's going on in the space, and that's important. So right now you have students that are assembling the physical parts according to the sort of pictures that they've seen online. And what's missing here is the electronics, like the Arduino and the power supply and the wiring is not in yet. That's happening at the next table over, being facilitated by another Uber geek. I'll tell you a little bit more about Andre in a second. But those students were more interested in the electronics parts, and the other students were more interested in the 3D printing and laser cutting side. So you're able to like sort of split the teams and work independently and then bring it all back together again. In the meanwhile, we'd made up a list of things that were missing that needed to be 3D printed. So we set them off on the side to print those while we figure out how to assemble the device. One special thing I wanted to point out is that this particular university was researching how to repurpose aluminium. For this particular city, the problem was that they had an excess of aluminium cans that were piling up, and they couldn't get rid of that waste in a meaningful manner. So they were experimenting, how do you take beer cans, melt them down within the space that you have, and turn them into useful objects. So this is what they were doing while the Braille machine was being printed on the site. And there is a relevant story as to why this is important, and I'll come back to that in a second, later on at the end. But that's how you recycle aluminium. You get a whole bunch of beer cans or Coke cans or whatever, shove them into a melting device, and then pour it into a mold. And you can do that with a small space where you don't really need to have large amounts of equipment to do that. So what you're able to do then is transfer the knowledge from one team to the next. The person on the right is very good with 3D printing. The kids on the left were very happy with taking apart devices that they would otherwise be scared to take apart. So they're the e-waste salvaging treasure making team. The ones in the middle were very interested in working with the metal, the hardware parts. They were experienced with doing woodworking and metalworking. And so what they did was round off the tip of a screw, which is what actually makes the dots on the paper. So each dot is just a rounded screw. It's nothing special or fancy. We go in there with a sample. We show this to the students and we say, okay, fine, come up with a way to make this happen. Here's the documentation if you need it, but how can you make this kind of a dot? So they made like 6 or 7 or 8 different things, had a lot of fun with the machines that was in the space, and they came up with a few options that made sense. Together with a 3D printing guy, they were able to put it together and make the machine work. So later on, have a look at the machine and see how that works. I have to point this out. One of the requirements of this challenge was to find ways to repurpose aluminium. So because the college was doing molten aluminium, they were looking to see whether they could use this machine to print on aluminium sheets. And it turns out that the sheets that you get from a beer can are soft enough that you can put it into the machine and it will do exactly the same thing that you're doing on paper. The advantage there is that it is waterproof, so you can stick it outside. Like you probably have noticed, like usually in lifts, when you have buttons, you have braille on it, and that's made out of metal. So if you have a cheap and cheerful material that's lying around, you can also do something like that without having to have it be manufactured. So you can do signage and wayfinding using beer cans. This was the favorite activity of this whole exercise. You want to guess why? Say again? You can reuse them, yes, exactly. So that meets the sort of like the brief. But the students enjoyed this activity more than anything else because the beer cans that we had were full of beer. So in order to make testing material, they had to be emptied first. And that's all I said as part of our, because we only had 3 days to build this thing. And this is something that never done before. So the whole challenge was 5 days. The first day we spent talking to the special needs schools and the teachers and the context, understanding where this would be used and why it would be useful. The next 3 days we just built like crazy. And then the last day we would have to pack everything up, put it into a bus, and then drive across for 8 hours across mountains to get to the capital where it would be showcased. So it was very intense. So everything had to happen in parallel. So this is the software coding process, which takes a lot of time and doesn't look very impressive on Instagram. So you have people sort of filling in and doing time-lapse photos at the back. But you know, the work that we do with writing code isn't particularly Instagrammable, but we try. Let me show you this little thing. All right, so once the device was barely ready enough to take over to the capital, we had to display this at sort of like a maker fair, science fair kind of event. And you can see here that it is printing on the aluminum sheets that were very carefully emptied out from beer cans. What I found very helpful or meaningful was the brief that was given to the students was, look, we need aluminum sheets to demonstrate at the event tomorrow. They took it upon themselves to drink as much beer as they could. But without being told, they also washed all the cans, cut off the tops, and cut off the jagged edges, and brought a stack of paper the next day. So it wasn't just about slagging off and drinking as much beer. It was they understood what the brief was. They understood why it was necessary. And without being told, they got it down to exactly the right size. So that kind of understanding is very hard to transfer if you're doing everything online. I think it's the value of being there in person is super helpful if you're able to bring people to the table and in a way that they understand why they are there, rather than just following a set of instructions. They're able to make the project their own. Because the intention was made very clear that, look, whatever we do here. It's not just for the purpose of the challenge. The purpose is that once these weird international foreign type people are done with their showcase, they go back to their own countries. But the device will live in Bhutan. And so it's up to the students to decide what to do with it. So right from the start, even before we joined the challenge, that was set out to be the case. And so I'm very happy that once this event was completed, the students went on to develop the project even further. But I'll show you that in a second. I just wanted to like loop back to the beginning. So you remember that image that I showed you earlier, the 2006 one? So the guy on the right who's holding the sign that says child is Vic Oliver. Does anybody recognize Vic? No. The guy in the middle, at the bottom, in Bhutan, is Vic Oliver. He just happened to be at the challenge. I had no idea he was going to be there. He had no idea we were doing this. He had no idea that the Braille Wrap even existed. But he's the guy who made the first RepRap child project back in 2006. So Bhutan was the place where it all came together. The students who were there immediately recognized the significance of having him over there. So they sort of jumped into his brain and to find out what he was doing. He, of course, that wasn't the only thing that he was working on. It turns out that Vic has been making other accessibility devices since then. What he's demonstrating on the right is a one-handed keyboard. You can, for the hackers among us, you might be interested in this. It's open source, it's 3D printable, uses a microcontroller that you can reprogram. Doesn't matter if it's Arduino, it can be an ESP32. With one hand and just 6 buttons, you can replace the entire 101 keys on your keyboard. It is possible to do it, and it's downloadable and it's open source. And that's the guy behind it, and that's the same guy who built the first RepRap. So it beautifully links everything together. But the thing that I want to focus on is the Braille side of things. If you're interested in getting connected with the other projects, do come and see me later on. I have a little table at the end, right next to the Hack Club guys. They're more noticeable than I am. But yeah, come and talk to me about that. I'll link you up. But these 2 pictures that I'm showing you are from a different event. This event took place 1 year after. And you can see this particular machine does not have the same cool stickers that the first one had. So this machine was built entirely by the students that we worked with. They only reached out to us when they were stuck with a particular problem, and we were able to help them out with just Zoom calls. So they have made another machine. They decided to do it just as transparent as the first one. It doesn't have to be transparent. You can make it out of plywood or MDF or whatever material is accessible to you. Any questions so far? Okay. How am I doing for time? Excellent, thank you. I think we're doing great for time. All right, jumping into a little bit more about lessons learned. I'll show you a couple more examples of the different devices, and then we'll go into questions. I would like for you to feel free to ask any type of question. No question is too silly for at least the next 25 minutes, okay? So the device that you're seeing over here is slightly wider than the one that I have. So this one can print on A4 size. The one that the students decided to build afterwards was even wider. But you want to guess why? Why did they make it bigger? Exactly. When you print dots on a piece of paper, each dot takes up more space than a printed out alphabet. So the amount of space, the amount of text information that you can fill into one page is quite small. So you need lots of pages. And if your page is bigger, then you can fit in some more information. And it turns out that the standard for textbooks that are made in Bhutan and most places that have Braille textbooks, they use a double standard. Instead of using A4, it's A3 or roughly around there, something in between. So it's a larger piece of paper that goes into the machine. And they were able to do that using the same resources that we used to make the A4 size. They applied their own skill and judgment to make the adjustments necessary. Because the files are digital, they're able to modify them. So the box of this thing is using vector files. And because they are laser cut, you can increase the size and then just cut them again. The parts inside are all 3D printed. Like, you saw in the previous picture, you can just make a box of these things and they're printing on the side. So if they don't quite fit or you need more of them, you can change the size and the shape of the 3D printed, the 3D model of the file and then print it again. So that's the approach that they took to make a bigger version. And what's happened then is that work is now back into the Braille Wrap project. So now there is a bigger version of Braille Wrap that's available. So if you are interested in the larger size, you don't have to redo the work. The work is already done and it's part of the main repository already. So there is an XL version of the Braille Wrap. It's still under active development. So if this is an area that you're interested in contributing to, now is a very good time to do that. So this looks pretty much the same, but it's actually much wider. Okay, so if you want to get started with, if you need the reference for all of the work that was done in Bhutan, it has its own repository. The links over here will take you to the repo. Later at the end, I will give you a QR code that's easier to scan. But the guy who was responsible for writing the software that we wound up using, Andre, who was working with the students with the electronics, he basically decided that the software that was available as per the documentation wasn't good enough. And this is, I think, something that is very FOSSASIA, or very FOSS community, where you see somebody else's software and say like, yeah, no, I can do better than that. So Andre did that, and he decided to rewrite the software in 3 days. And he did. And it works. And it's mostly written in TypeScript. Who's done TypeScript? Yes, outstanding. Okay, so if you look at the Braille Wrap UI repository, it's all done in TypeScript. This opens up 2 new opportunities, which is that if you want to change from English to say Bhutanese, or even Thai, or French, or any other language, all you have to do is go in and change the language file, and you're good to go. Everything else will work. The software is open source, and so you can change whatever you need to change. This is the QR code. Will take you to the link for all the resources that we put together. The Braille machine was just one small part of the aluminum recycling things that we did. The team actually came up with a whole bunch of resources for helping children with disabilities and special needs. What you're seeing on the left is a map of where to find other instances of this device. And if you zoom into the Southeast Asian side, you'll see that Thailand is not part of that map yet. So my hope is that at the end of this session, you will help find somebody in Thailand who is interested in replicating this project. By interested, I mean we have a use case, meaning that it is actually going to help somebody who can read Braille and print Braille. That would be amazing, yes. So just keep that in mind, and if you have a resource, then I'll be happy to talk to you more about that later on. All right, so talking a little bit about the Singapore context. I'm based in Singapore, and the group that I mentioned, Salvage Garden, we operate out of a public library. Singapore is lucky in that we have public libraries where 3D printing is available to everybody. There are only 4 library branches. This is the newest, shiniest, and the coolest looking. You might have seen this because it looks very Instagrammable. So a lot of these pictures have been floating around, but it's a 5-story building. The first 2 levels are for kids, and then you have teenagers in between, and then you have the adult section on top. The makerspace that I do most of my work in is on level 4, which is the adult section. But what I want to point out is special, apart from it looking Instagrammable, is that it's accessible. It's designed for accessibility. And not just wheelchairs and access ramps. We're talking about all kinds of disabilities. Disabilities that might not be visible. So yes, it does cater to people with visual impairments and audio, hearing impairments, but also intellectual disabilities and so on, which might not be obvious at first, but this is a very good example. So if you're coming to Singapore to visit Salvard Garden, also have a look at the library. It is totally amazing to come and see. So this is what our space looks like, to give you a sense of how we do our work. It's nothing too fancy. It looks a bit like a classroom, but over the wall in the back, you can see there are a whole bunch of 3D printers. Those machines are available to the public, meaning that anybody can go in and book some time and print whatever they want. It doesn't have to be like for printing things for people with disabilities. You can just print keychains, you can print decorations, you can print like birthday gifts, whatever it is that you want. It's part of the library. But on Sundays, on weekends, this volunteer group comes together and we sort of take over that space and we focus our efforts and time on more meaningful projects and helping persons with disabilities. So that's our context, and that's where we sort of assembled and built this machine. And to my knowledge, this is the only machine that has ever been built in a library. But if you know somebody else who has, please let me know. I'd love to work with them. But so far, yeah, we seem to be unique in that aspect. I mean, whatever that means. What we learned from Singapore that is quite strange and might be useful for you for other projects is a lot of the parts that are inside here, sometimes they are hard to find for whatever reason. In Singapore, it wasn't that the parts were hard to find, it's just that I was working with some students who didn't want to go and find the parts. So they, instead of going to the store in Bugis and Simlim, they went online to search for something that they can print. And I was very skeptical of this because the parts that they were looking for was this black belt that moves the head left to right. And the belt is very commonly found in 3D printers. But it turns out that you can 3D print it. And because these students had access to 3D printing, they tried it out. And I was very skeptical, but it turns out it worked. So if you need a belt, a GT2 belt, which is quite common for like moving things around, you can print it out of TPU. And it works, which is quite surprising. This was helpful for the Bhutan team, even though they had plenty of belts to work with. Knowing that you can 3D print a belt like that makes it that much easier to try new things out. So this is what our setup looks like. The people in Singapore, they really do like unicorns and rainbows. So we try and decorate our devices with as many stickers as we can. This is the second device. This is the first one. All right. Very quickly, I'm going to show you an example in the Philippines. This was, again, just to show you the differences between how we do things in Singapore versus how I showed you in Bhutan and how this looks like in the Philippines. I hope you find that informative in making the necessary adaptations for your local context. It might be that you are connected to a makerspace in a company or makerspace in a university, which might not be publicly accessible. And if you've been to more than one makerspace, you know that they are completely different. Some places have 3D printers, some places have laser cutters, some places are incredibly loud and noisy with woodworking. Some places are incredibly smelly with like metalworking. Other places are very neat and clean and shiny like the mold makerspace. So this little makerspace in Manila is actually sharing the space with a furniture manufacturer. So they are doing things like 3D printing lamps, and that's how they're able to sustain themselves. But they were interested in doing like a meaningful project, applying their skills towards something more meaningful. And so I was able to build this machine together with those people. There were just 3 people who were working with me on this, and we were able to do it within a week. The team in the Bhutan was much bigger, and they were all engineering students. But in this case, we had some accidents. Does anybody recognize what's in the red circle? So what you're seeing is an Arduino. It's not the official Arduino. This is what we call the China Special. But it's hard to see in this picture, but this point here, yeah, yes, that's where the magic smoke comes out. So while we were connecting up the wires, the plus and minus was reversed. And so it was like a puff of magic smoke. So then became a question of like, where do we go to get a replacement Arduino? Because this makerspace doesn't do electronics. They only do 3D printing of lamps and furniture. So then we went out hunting for electronic stores because we only had a short period of time. We found a hardware store, which is great, but no Arduinos. And the thing that actually we needed, luckily I brought along an extra Arduino, so it's fine. But the thing that we needed to prevent the magic smoke from being released again was a diode. And so we weren't able to quite find that. We also didn't have access to wires. Does anybody recognize this? Yes? And if you've done Ethernet cabling, you know that it has pairs of wires. And instead of going out and buying single wires, the hack here was you take an Ethernet cable, cut it apart, and you've got lots of wires. And what's beautiful is they're usually color-coded. So instead of going out and buying different wires of different colors, just buy one of these cables and cut it up. Which is a brilliant hack. We were able to get back on the road. You can see the hack on the top right corner. It repurposed quite a lot because no electronics. And that's actually the same board that we have here. So you can come and take a look. So those are the 2 wires that got short circuit because it didn't have any insulation. All right, so that was one learning from the Philippines. The other thing that happened was the person in the picture, because he was employed by this makerspace to 3D print lampshades, which was how they sustained their space. He was like, look, we don't have a laser cutter. Can we just 3D print it? So instead of laser cutting the outside and having access to a laser, what he did was spend that time redesigning the laser cut parts so that they can be 3D printed. So if you have just one machine instead of 2 machines, you now have a starting point for 3D printing your way out of not having access to a laser. So the files for this particular model are not publicly available yet. He's a bit of a perfectionist. He wants them to be just right before he uploads them. But there is an option that is available. Somebody's actively working on it. If this is something that you need, let me know. I'll link you guys up. The opportunity here is then you can have like an entirely 3D printable version of this box, which will be accessible to some people. You'll see the patchwork over here is a little bit weird because the printers can't really handle this large of a space. Most of the commercially available printers are able to handle about half. And so what we've done is work around that problem, print them in 2 halves, and then stick them together. So if anybody's done 3D printing, you're probably already familiar with this. But those who haven't, this is a wonderful way of jumping into printing things that are bigger than your printer. So this is what the machines look like. You have the Singapore version standing next to the Philippines version. We followed the same instructions as before, the same ones that we did in Bhutan, and make the necessary adaptations as we go. And when you have a working version that is transparent sitting next to you, it's a lot easier to accelerate the building process. I mentioned in the brief of this talk that there was another country that normally most people don't think about, Cameroon. So the reason I was in Manila was not to actually build a Philippines version of it. It was for a particular conference similar to FOSSASIA, where it was called the Build Peace Conference. And we had a delegation from Cameroon who wanted to build a machine. So instead of us building it in Singapore and just sending it to Cameroon, the invitation was, come to the Philippines, we'll make one over there, and you can learn from that experience and take back the knowledge on and whatever parts you need. So instead of giving it to them, it was a knowledge exchange exercise. And we basically used the funding for the conference to make that happen. So it's a bit of a hack. If you're keen on finding funding for this kind of thing, you sometimes have to work with whatever you have. So this device is here now. It wasn't sent to Cameroon, but the team that learned from the experience is actively now working on building one in Cameroon. So if anybody has connections there and is keen on doing this, please let me know. I'll connect you up. This is what came from the Cameroon exercise. They didn't have enough time to actually spend building the thing, but during our time in the conference, we were able to replicate the online repository, the one that was built in 3 days by that one guy. So the Bhutanese version is now hosting the software side for the Cameroon side, and everything links back to GitHub. So if you're looking for a place to start and you're shy about jumping into the hardware side, and you're comfortable with the software side, just replicate the front end and you'll be fine. It'll be a good place to start. So the underlying message behind all of this is try to be inclusive, not in the sense of like thinking about disabilities specifically. My request is that you think about how to include people that are not otherwise comfortable with doing what you are already comfortable with. So you might be very good at software, somebody else might be really good at Arduino, somebody might be really good at 3D printing, somebody might be really good at documentation, social media, teaching, finding ways to communicate with people with different disabilities. All of these are valid ways of contributing to the project. It's not just about bits and pieces, downloading things and contributing to GitHub. Try and step away from that model as much as you can. That's kind of what we're trying to do in Singapore, and we seem to be having a positive influence. This is something that I learned, that we can't do this. We can't put up a sign outside the library that says, no douchebags allowed, because that's not inclusive. But that doesn't mean that we invite douchebags into the process. And it doesn't mean that we celebrate them. And it doesn't mean that we stop listening to everybody else just because somebody is screaming their heads off. But we can't put up a sign that says no shouting. So we're still struggling with this. How do we be an inclusive space without having to resort to weird exclusive policies like this? If you have ideas of how to go about doing that, please do let me know. But I am a tech person, so I rely on my tech background to see how I can learn from the models that I'm familiar with in the tech space and apply them to what I'm trying to do in the inclusion space. Is somebody familiar with this model? Okay, excellent. This is now achievement unlocked. You're now familiar with the community side of open source projects. We're all comfortable with GitHub and repositories and handling conflicts and resolving conflicts as far as the code is concerned. But the user side is something that we can now look at a little bit more. So these are roles that otherwise you wouldn't normally think about in an open source project. But in order for a project that is open source to succeed, you need to have these kinds of users. So like I mentioned earlier on, you might have people who are interested in the bits and pieces, the tech side of things, but you also can include people who are teachers, educators, caregivers of persons with disabilities. All of those people have an opportunity to come and join in. So just the same way that we would consider different users and different roles, try and consider people who are not necessarily tech people and bring them into the co-creation process. So that's the formula, the magical formula that we've been applying. And I strongly recommend trying this out. We've been doing this for 2 years in Singapore, and it's working really well. It's creating a lot of impact. It's incredibly meaningful work. We take the idea of digital fabrication, which is 3D printing and laser cutting. We combine it with open source, which is like repositories and things that you're familiar with. And we introduce this idea of co-creation, where instead of you making for somebody and then just delivering it, you ask that person to come in, sit next to you, and then you make it together. They might not actually have the skills, but the fact that they're sitting next to you makes all the difference in the world. Okay, move on. All right. So now for Thailand. The question now is, how might we learn from this particular project and invite participation from people that you interact with locally and see if there is a need for this. We were very fortunate with FOSSASIA yesterday. I got to meet a very impressive group of young people who are also in the room, which is excellent. The Hack Club people presented their work yesterday, and a small group of students has expressed an interest in making one of these devices. Initially, I thought that I would have to like do a lot of outreach work before I found somebody, but we already have interest, which is great. So if we can build on this and amplify it, it will be amazing. The students who are interested in doing this as part of their coursework, I imagine, will need all the support that they can get. So if you can do that, speak to Hack Club. They're right next to me in the exhibition area. Also wanted to point out, there was a gentleman from Cambodia who stopped by, and he has built a web-based translator that can do Khmer to Braille, and it has no connection to the machine that prints it out. It's basically just a translation app, and this was funded as part of some other project. But he immediately, when he saw this machine, he was like, this is amazing. We can combine these two ideas together. So this, I don't know if it is open source or not, but because ours is based on TypeScript, if somebody is interested in putting the Khmer character set into it, there's already a need for that now. There's somebody who wants to make this happen in Cambodia. All right, so just to wrap up, bringing it back to what we started off with, there's a lot to the Braille beyond just the language. Even though Braille is something that we like to talk about, and it's been around for so many years, the way most people who are visually impaired or blind, they navigate their day-to-day is using screen readers. They listen to what is being displayed on the text on the screen, much the same way as we would rely on looking at what's on the screen. So it's mostly audio-based. So things like audiobooks and screen readers do most of the work, but that doesn't mean that there is no need for printed materials. The same way that, you know, just because we have our screens now, we stop printing things on paper. It doesn't happen that way. The same thing with the Braille. The need for the printed material has transformed. It has not been replaced. So that's something I just wanted to point out. The software can do shapes, which is different from just text. And the text that you were seeing that in the initial example, if you look a little bit closely, you'll see it's not in English. The names of these animals are in French. So when you look at them in Braille, you can't really make out because you're using your eyes. Okay, so that I just want to wrap up again. That's the Braille Wrap XL. That's the Braille Wrap A4, and that's the version that I have here. Given the time that we have, I don't think I can go into like the team building exercise. What I will do instead is I'll plug this device in and run the software on my machine. So you can come and try it out, ask questions, and then we can go that way. Is that okay? All right. Right. Thank you.
suggestion to kind of have printed out material sort of fed back into the machine so that it can kind of continuously print something over time? Should that be something like a useful modification?
Like printing back on the same material that went through the machine.
So that it can kind of reset the material at the same time, print again over what was already printed on previously.
Interesting.
Like reverse.
I hear what you're saying. For that, you would have to erase what was already printed before, right?
Erase or use different material, like certain kinds of plastic. Kids have these machines for
Yeah.
press
Yeah.
and then press back. So
Yeah.
something as flexible as that.
Silicone.
Can be overused too much over time, but
Yeah.
Can be resilient enough to keep going.
Yeah. I think that's an interesting idea. You can develop that separate from this device. You can probably borrow some of the ideas from here and then apply it on a larger scale. But in our case, we want to use low cost and accessible materials. So yeah, it's a one-off process. But that's an interesting idea.
I don't need Mike. How is the TypeScript, obviously you probably use React, but how is the TypeScript integration with the hardware? Is it tricky? Because I'm seeing a little bit more TypeScript-based IoT stuff happening.
Yeah.
Is it like, somebody drink a lot of coffee for
Yes.
a few days?
Yes.
Yeah.
But the advantage we have, I'm not the right person to answer this, but the advantage we had was web serial.
Yeah, there is a React package, some serial, but I'm sure there's something else too. Yeah, it's something I've kind of been looking at. So it's like, for serial printers. So I'm curious how you approached it, because try to look at looking and even using AI as a crutch to answer questions. There's not a lot of it.
Yeah, no, you're absolutely right. The area is still relatively new because the web serial module is still relatively new. But the advantage we have and the thing that's driving its development is all of these new microcontrollers that are being used in schools. So the PVC microbit is very common at the primary, secondary school level. That's how kids are now learning how to do programming. And in Singapore, this is very commonplace. There is a web version so they just open the thing that in the browser and then connect it and program it accordingly. So it simplifies the process. You don't have to muck around with drivers. So as long as the USB device is recognized as a USB device, then you can handle all of the protocol levels within the web stack. So that is a distinct advantage now that we didn't have access to before. Yeah. Yes. So yeah, as long as the is recognized by USB by the system, then there are options available for TypeScript to take over. Yeah.
Just wondering how you send the files, like in what format. For example, in the case of 3D printer, you will have the object, the SQL file, then you need to somehow convert it to G code so the printer can print.
Yeah.
I guess it would be similar here, right? So you would have some sort of source file that has to be translated to G code.
Yeah.
And then you get the G code there, right?
Yes. I think you've just answered your own question. But
yeah, but I don't know what kind of file you use as source and what is the translator program that you use.
So the web interface takes in text. So you type in text here, for example, and you hit generate. When you hit generate, you'll see the dots on the right-hand side. These dots are the arrangement of where this machine needs to move and make an impression. And because this thing moves and presses one dot at a time, one row at a time, it follows exactly the same instructions that you would give to a 3D printer. Except in this case, we don't have the 3 dimensions, we only have 2 dimensions. So you've got left and right and top, up and down. So that's 2. And then for making the impression, it's just an action either on or off. So it follows G code.
So this is almost identical code.
It is G code. It is exactly G code. So what this web application is generating is G code. So it shows you what the G code looks like here in terms of dots. But when you hit print, it will send that G code as G code over the USB serial to this machine. And because this machine uses the same firmware, Marlin, that reads G code and interprets G code, it is exactly that. So there are other web-based software that you can use to generate G code like this.
So the code idea of the printer is exactly the same.
Yes, it remains exact. Yes. So in the case of Marlin, there are some modifications, mostly to turn off the things that we don't need. So the Z-axis is not relevant anymore. So the flavor of Marlin that we're using here is a limited version of the main 3D printer. So if you're familiar with Marlin, then you can probably make the same modifications again from the original source. Thank you. All right. Thank you very much. Einstein.
I like your.
Without that, nothing works.
Yeah, conversation is with Kia. Showed me the thing. So then Kia must have paid millions of dollars for that big box 3D printer they had.
Yeah.
Like,
Yeah.
because that's the same time those guys came up with their child.
Yeah. So before that,
I've seen that. Like, it's weird that that's like an art of. Like, I remember that like significantly because the guy would print them out right into our apartment. All these like whitish plastic opaque.
Yeah.
The chess pieces.
Yeah.
The geometric shapes.
Yeah.
No,
It's not that far behind.